Today I'm going to wrap up our discussion on the semiclassical theory, in which semiclassical theory means that light, which is electromagnetic radiation, is interacting with a two-level quantum system. And the motivation for this lecture is twofold. First of all, I would like to bring together two words. One was the word of Einstein, whose rate equations predicted an n2 over n, which is of this kind, right? This is something you also read in homework number 1, question number 1. So Einstein's rate equation predicted that the population of the excited level increases linearly with time, and then it saturates to a certain value. This saturation value depends upon how much energy density is available at a particular frequency, you may or not. So if you shine in a lot of laser light, which means that u omega approach to infinity, this was 1/2. Right? So at best you could get half of your atoms to be in the excited state if you shine the atom with very intense laser light. But then the problem is, this is slightly paradoxical, because these equations only hold true in the weak coupling limit. But nevertheless, the Einstein rate equations predict an evolution, a dynamics, such that as time goes up, the population of the excited state asymptotes to a maximum value, and that maximum value depends upon how much light density is available. If the energy density at omega naught approaches infinity, then this maximum value is 1/2. Homework number 1, question number 1. So this is from Einstein's rate equations. That's at best what you could achieve. However, about 2 lectures ago, we also discussed Rabi oscillations. Now, Rabi oscillation was a complete inversion. If you had on-resonant radiation, no damping, then you would get a complete inversion from ket A to ket B. Correct? So all your states would go into the excited state. And we came up with a formalism such that we could really go all the way up till 1 and get these nice oscillations between the excited and the ground state. Alright? So this is from Rabi. Now, which of these pictures is correct? So these pictures must reconcile, they must be correct in their own right. So now we have to reconcile the 2 pictures. And in order to reconcile the 2 pictures, one factor which was ignored previously has to be kept into account, has to be factored into the equation. And that is the role of damping. We've already seen how a classic oscillator damps, and that models spontaneous emission. So let's look at this problem in a more careful way. Now, if you want to look at damping, we know that on the Bloch sphere, if there are states that are progressing, and if they remain on the surface of the sphere, then it must be a pure state, and there will be no damping. However, if the state kind of collapses and goes into the interior of the Bloch sphere, there must be some damping. And a pure state cannot describe such a state. Therefore, we resort to the idea of density operators. Now, it's a 2-level quantum system, so our density operator is a 2x2 matrix, which has these terms: rho AA, rho AB, rho BA, rho BB. Correct? Rho AB is CA CV star, rho AA is CA mod square, This is CBC A star, and this term is CB mod square. Okay? And our quantum state as a function of time for the two-level system is some CA T ket A plus CBT ket B. Correct? So now this state, if you take the outer product of this state with the corresponding drive, you get this density operator, right? So this density operator is formed by this outer product, right? Now what we would like to do is we would like to, previously we wrote down we solved the time dependent Schrodinger equation, and we were able to write down a pair of coupled equations. Now those equations read as follows: ECAODT is I Rabi frequency, right? और क्या था आगे? इसको याद है?
डिवाइड बाई 2 भी था.
Divide by 2 और आगे E plus I omega minus omega naught T CBT, correct? This is our first equation in the rotating wave approximation. Equation number 1. And our second equation was dCd is I omega r over 2 E minus I omega minus omega naught T CA T. ये वाली इक्वेशन अभी कोई फील्ड स्ट्रॉन्ग या वीक नहीं है, इसमें अप्रोक्सीमेशन रोटेटिंग वेव अप्रोक्सीमेशन, ठीक है? All right. So now in these equations, what we would like to do, instead of the time evolution of the coefficients, we would like to find out the time evolution of the density operator matrix elements. Alright, let's first include the impact of damping. And the kind of inclusion that we are envisaging is a kind of is not totally accurate, but it's what is called phenomenological damping. Since damping is an acoherent process, the modeling of damping is not very straightforward. Sometimes you need a master equation called a Lin-Paul master equation to accurately predict damping, but for the purposes of understanding, it's nice to have a phenomenological model, which means a model that works in most cases. Okay? That will give you a better understanding of what's going on. So in order to do that, what we assume is that if I have two levels, ket A and ket B, then if there is a non-zero amplitude in ket B, which means CB is non-zero, an atom is in this level, it has this propensity to decay, and when it decays, it gives off photons through spontaneous emission. Okay, so this decay is really spontaneous emission. Those photons are emitted in all possible directions. So the decay process is isotropic, and this leads, if you look at the spectrum that comes out from this atom, this leads to the broadening of a line, delta omega. This delta omega is inversely proportional to the lifetime of this state. Okay? And this delta omega is also proportional to a decay rate. Okay? Let's call that decay rate gamma. So, longer the lifetime, smaller will be the decay rate. This is a kind of decay rate for spontaneous emission. This is the rate at which N2 levels are depleted and they give out photons by spontaneous emission. Okay? Now, in order to model this, a nice thing, so this is Lorentzian, which means that this decay rate is properly modeled if in this equation we include another term which corresponds to gamma. And what would that term look like? That term would look like the following: dCB over dt is equal to iota omega r over 2 e minus I omega minus omega naught t c a t minus gamma cbt. Right? So we already know that. Why have we put in this equation? We already know that if we have something of this kind, dy over dx is minus gamma x. The solution to this is x equals x naught e minus gamma t, correct? So if you can model damping,
वो y नहीं होना चाहिए,
जी।
गामा का y नहीं होना चाहिए,
why?
क्योंकि तब भी e
gamma के साथ क्या होना चाहिए?
नहीं उधर dy by dx में इक्वल टू माइनस गामा.
Oh, gamma y. Sorry. यहाँ x आ जाएगा. Sorry. Okay. So this equation has a solution of this kind, a decaying exponent. This is the decay rate. So motivated by this equation, we can insert an additional term which accounts for damping, which accounts for the exponential decay of Cb. And that term is given a minus gamma Cb. Yes, please. यहाँ पे कुछ भी नहीं कर रहा, सिर्फ ये y वेरिएबल है. dy over dt अगर माइनस gamma y के बराबर हो, this means that my y is an decaying exponential. ठीक है, y को आप cb ले लो. अगर dcb by dt minus gamma cb के बराबर है like this, then cb will be decaying with time. Okay. So I have put in this factor by hand, okay, which accounts for a decaying Cb, and that decay rate will be gamma. So now I have two equations. One is equation number 1, and the other is equation number 3. Ji.
What is the term like damping is from like term is damping is from like ठीक है वो decay like show करता है अगर हम इसका लेकिन with respect to time लेकिन decaying जो है वो damping को कितना show करता है.
तो जो damping है वो decay ही तो है. damping का मतलब है decay. कि जो excited state में जो population है वो कम हो रही है वक्त के साथ साथ, इसको हम damping कहते हैं या decay.
लास्ट लेक्चर में जो हमने वो जो डिफरेंट नॉइज ये थे पोलराइजेशन और डीपोलराइजेशन और
हाँ वो एम्पलीट्यूड डैम्पिंग. ठीक है, ये एक एम्पलीट्यूड डैम्पिंग भी है और इसमें एक फेज डैम्पिंग भी है, because this will cause a decay of both of these populations as we will see, and it will also cause a decay in the coherences. So it has both kinds of decay.
So what do you mean by
off diagonal when you say coherences?
So these terms are called populations. Rho AA is Ca mod square. It's proportional to the number of atoms in the ground state. Rho BB is Cp mod square, is proportional to the number of atoms, fraction of atoms in the excited state. And C is Cp star is a term which can be complex. This can be complex. This has no classical analog. This only exists for quantum systems. And this term can vary with time. These terms, these off-diagonal terms, are coherences. And remember, this is a legitimate density matrix, which means two conditions are satisfied. One, the trace of rho is 1, which means that the sum of these elements must be 1. And it's Hermitian, which means this term is the complex conjugate of the other coherence. These terms are coherences, these terms are called populations. Okay? And the eigenvalues of this density operator are non-negative. Okay? ठीक है? इनको coherences कहते हैं. Now let's look at these equations. So first of all, what we would like to do is I would like to calculate the rate of change of the excited population. So I would like to calculate the derivative of rho BB. Remember that rho AA and rho BB are real numbers because they are populations and they are modular squares. So I want to calculate this, which really means I want to calculate CB star CB. This means, so I just do the chain rule, star dt CB plus CB star dCB by dt. Okay, now I look at this equation and just insert these values. So what I do next is I assume that this thing is delta omega. Delta omega. Okay, I just shorthand I write this is delta omega. So my derivative of the excited population becomes rho BB. This becomes, take the complex conjugate of this equation, minus I Rabi frequency over 2 E plus I delta omega T Ca star Cb minus gamma Cb star Cb. Correct? Plus Cb star multiplied with that object plus I omega r by 2 E minus I delta omega t Cb star Ca minus gamma Cb star Cb. Correct? Correct? Now this term and this term, so I combine these terms, I get minus I Rabi frequency over 2 E plus I delta omega t. This is rho AB star, which is rho BA minus, this is Ca Cb star, so it is E minus I delta omega t rho AB minus 2 times gamma Cb mod square, which is rho BB. Right? So notice that the coherence is decaying. Cb, the amplitude is decaying at the rate of gamma, and the population is decaying at the rate of 2 times gamma. So nice. Okay. Now I would like to do another substitution. I move to a rotating frame. Now the coherences are rotating. Observe the coherence here is rotating at a frequency which is equal to the detuning frequency. So I replace this thing by rho AB tilde. This is, I move to a frame in which this time dependence is halted. So I'm moving in a frame that is itself rotating the detuning frequency. Okay, this is going to an interaction picture in quantum mechanics. So just remember that I'm making a substitution of rho AB into this term is rho AB tilde. Now this is the complex conjugate of this. So this is rho BA tilde, right? Okay? This means that my derivative of rho BB equals minus I Rabi frequency over 2 rho BA tilde minus rho AB minus 2 gamma rho BB. Correct? So now I have an equation for the time evolution of the excited state population. Now the sum of these terms is 0. So the derivative of this must be equal to the negative of the derivative of this. So this must equal minus d by dt rho AA. Okay? So, which means that the evolution of the excited state population is not independent of the evolution of the ground state system. Because it's a two-level system, there are only two levels in the system. By the way, rho BP tilde is the same as rho BP. I also make this substitution. Rho AA tilde is the same as rho AA untilde. Okay, these are substitutions that I make. I can make this choice. Now let's look at the what we would like to have is, in fact I can also write this as I omega r over 2 rho AB minus rho BA minus 2 gamma rho BB. This is the same thing. Now let's calculate the rate of change of coherence. Now this is the rate of change of a population. Now I'm putting everything in terms of the density operator because I want to allow for damping to take place. Okay? Now let's find out the rate of the change of a coherence, say rho AB. In fact, let's look at the rate of change of rho B tilde because I want to put everything in the rotating frame. I want to do everything in the tilde frame, in the rotated frame. Right? So now this thing is d by dt. Rho AB tilde is defined as E minus I delta omega T rho AB. This thing is minus I delta omega E minus I delta omega T rho AB plus E minus I delta omega T d rho AB by dt. Okay, but this thing again is rho AB tilde. So my derivative of the rotating coherence is minus I delta omega rho AB tilde plus E minus I delta omega t, the derivative of rho AB, which is CA CB star. Now this thing has to be determined. Need to determine this. So let's determine this in another step. So d by dt CB star is the derivative of CB star plus CA, the derivative of CB star dt. And the derivative of CA is given here. Iota gamma r by 2 E plus I delta omega t, the CB mod has become CB mod square plus CA and the derivative is CB by dt. This thing over here. All of this is E minus I delta omega t CA t minus gamma CBT minus gamma CB, right?
सर हमने वहाँ पे CB और T में हमने डिकेइंग फैक्टर ऐड किया था, तो सर हमें CA में एक इंक्रीजिंग फैक्टर नहीं फिर ऐड करना चाहिए, क्योंकि अगर वहाँ से डिक्रीज हो तो CA में इंक्रीज होगा।
अगर आप देखो ना डी रो ए में देखो डी रो, अच्छा सवाल, इट्स वेरी गुड क्वेश्चन. Phenomenologically you don't have to do that, because if you look at d rho bb, this is minus 2 gamma ib. If you look at the derivative of rho a, it already has a plus 2a, 2 gamma in it. Okay.
लेकिन सर यहाँ पे जब हम
यहाँ पे भी आ जाएगा, देखेंगे, ठीक है? So now this is, but that's a very good question. So let me kind of expand this a little bit. This is I E plus I delta omega T rho BB, right? This is rho BB plus I gamma R over 2 E minus I delta omega T C A mod square minus gamma, एक मिनट, ओहो यहाँ पे माइनस आएगा ना, पावर में प्लस सी ए स्टार ऐसे होगा ना, प्लस सी mod square, ठीक है, माइनस गैमा सी ए सी बी mod is rho a b, correct? ठीक है. Now I want to put this expression back in here to find out the rate of change of this coherence. Okay, so the derivative of rho a b tilde is minus I delta omega rho a b tilde plus e raised to minus iota delta t into all of this, so I get plus omega r rho bb. Rho bb can be written as rho bb tilde minus rho a tilde minus gamma e raised to minus I delta omega t into rho ab is rho ab tilde. coming up with rho AB. This shows that the coherences decay at half the rate as the population. Because the population decay occurs at the rate of 2 gamma. The coherence occurs at the rate of gamma. So each coherence decays at the rate of gamma, and each population decays at the rate of 2 gamma. Okay. So this is how the density matrix is built up. Okay. So because remember, the population is a modulus square. So the coherence is not a modulus square. So this gives me the rate of the decay. I can also express this as minus I delta omega rho AB plus omega R over 2 rho BB minus rho AA minus gamma rho AB. Now what I've done is I've achieved something phenomenal. I now have a rate of decay for a population. In fact, for both populations in one go. And I have a rate of decay for the coherences. Now each coherence, by the way, is a complex number. Population is a real number. So if I want to ease things out a little bit, and I want to see how different objects vary with time, I could define I could make some simplification. So what I could do now is I like to work with real numbers. Right? If you do recall that this density operator over here, any density operator for a two-level quantum system, remember, can be written as a sum of Pauli operators with real coefficients. Okay? Anything can. So rho can be written as identity over 2 plus sum A sigma x, right, plus sum B sigma y plus sum C sigma z, where A, B, C are real numbers, correct? Any two-level quantum system, the density matrix can be written in this form, where A is the trace of rho sigma x
फिर डिवाइड बाय 2 नहीं होगा
divided by trace of sigma x square, which is 2.
फिर
9. These are all traceless operators. Sigma x, sigma y, sigma z are traceless operators. The trace of this rho only comes from this term. All of them are traceless operators. I don't know if there is a 2 here, but this is trace of sigma x squared,
which is identity.
which is 2. So therefore there is a 2, etc. Okay. So any density matrix can really be written as a sum of 3 real numbers. Any quantum state, pure or mixed, can be identified in terms of these 3 real numbers. These 3 real numbers form a vector, which is called a Bloch vector. Remember that a pure state is one for which trace of rho square is 1, which is 2 for a pure quantum state. And if this is less than 1, it's a mixed state. Anyway, this is what we have for density operators. Now what we would like to do is we would like to define a variable u. Let's define a variable u, which is a real number. Rho AB, which, and I want to make this rho AB plus rho BA. These two elements, I want to add them up to give me the real part of rho AB. Let's call this u. Okay? This is a real number. This will be half times the real part of rho AB. Right? I add the number to its complex conjugate, I get a real number, which is the real part of this, of course with a half, with the 2 times, sorry. Okay? So I define this new variable u, which is now a real number. And I can also define a v, which is the difference of these numbers. So with the tildes, of course, and divide by I. Now v is also a real number. Rho AB minus rho BA is the difference of a number with its complex conjugate, which is iota times the imaginary part. So this v is just the imaginary part of rho AB with a factor of 2 perhaps. Right? So v itself is real. Okay? So I define these two new variables and they kind of convert the two coherences, which are complex numbers, into 2 real numbers. Okay? And those real numbers you will find can be expressed as A and B. One will be the sum of A and B and one will be the difference of A and B. This will be a homework problem. So how are U and B related to A and B? Okay? They will be related. Now, I define another term, W, sometimes called the inversion factor, and I define this as rho PB minus rho AA, which is kind of an inversion parameter. If this is 1, this means that only the excited state is populated. If this is minus 1, it means only the ground state is populated. So now I want to with these substitutions I would like to put in here. Okay, so first of all I would like to see what is my du by dt. Now du by dt is the derivative of this plus the derivative of this. The derivative of this is the complex conjugate of this. So I take this thing and add to it its complex conjugate. Right, so let me do that. So I take this first term and add to it the complex conjugate minus I delta omega rho AB tilde plus I delta omega, the complex conjugate of rho AB tilde is rho BA. Rho BA. Plus I omega R over 2 W, this is W, minus I omega R over 2, the complex conjugate of W is W itself, where W is real. Minus gamma rho AB plus rho BA. So this will become minus I delta omega rho AB minus rho BA. Rho AB minus rho BA
minus iota V
will be iota V. This will just cancel out. Minus gamma rho AB plus rho BA U. एक्चुअली मैंने यहाँ टू डिफाइन करना चाहिए कि नहीं, मैं यहाँ पे टू डिफाइन कर लेता हूँ, ठहरा मैंने ओमेगा बी माइनस गामा यू। This is one equation in U. Let's call this equation number 2, 3, 4. चलिए देखो मेरी 2 का फैक्टर तो नहीं मिस हो रहा। तो नहीं rho AB is 1 over iota rho AB, the derivative of rho AB minus this. So I want to take first of all minus I delta omega rho AB tilde. Let me first of all write all of this plus iota omega r over 2w minus gamma rho AB tilde. And from this I need to subtract. What do I need to subtract? I need to subtract rho BA, which is the conjugate of all of this, right? That conjugate is plus I delta omega rho BA minus I omega r over 2w. Now don't confuse this w with an omega. Minus gamma rho BA. Okay? So let's see if there are any cancellations. No cancellation here. No cancellation here. No cancellation. So, okay. 1 over iota minus this. So this is minus I delta omega rho AB plus rho BA, which is U. Plus I gamma r by 2. This is plus I gamma r by 2 w. With the I gamma r over 2w plus I gamma r over 2w minus gamma rho AB. This is rho AB plus rho BA. This is plus rho AB minus rho BA. Rho AB minus rho BA
minus iota B.
This is iota B, right? So this gives me, so this I, this goes away. Finally, dw by dt given by d by dt of rho Vb minus rho Aa. Now, where is my dE rho? There it is. So, this is d rho Vb minus rho Aa.
वही नहीं आ
वही
जाएगी
आ जाएगा, ठीक है, 2 times. So I'll get I gamma r rho AB minus rho BA, which is I B minus 4 rho BB. So let's express rho BB in terms of W. Alright. So we do know that rho BB minus rho AA is W. But we also know that rho AA is 1 minus rho BB. So 2 rho BB is W plus 1. Meaning rho BB is W plus 1 over 2. Right? So instead of rho BB, I can write rho plus 1 over 2. I get 2 here. Omega plus 1. So these are my 3 equations. Number 6. Yes, please. हाँ जी बिल्कुल. हनी जरा उसको कहना जरा बैटरी बिल्कुल एक्सप्लेन कर. देखें, we know that rho BB minus rho AA is W, but we also know that rho AA is 1 minus rho BB. So I replace rho AA by 1 minus rho BB. I get rho BB minus 1 plus rho BB. 2 rho BB is W plus 1. Okay. So now I have these 3 equations. Equation number 4, 5 and 6. These are differential equations in terms of the real parameters U, V and W, which are related to the Bloch vector. And they are real numbers. And everything is real here. On the left hand side, the right hand side, everything is real. So now I have a classical differential equation. These 3 equations are much easier to solve than the equations of the density operators, of the elements of the density operators. These are called the optical Bloch equations. Optical Bloch equations. Equations 4, 5 and 6. These are the optical Bloch equations. And if I want to write them, I can write them as d by dt of U, V and W. Right? This is given by a vector. Okay, so I can write these equations in the form of minus omega r 0 delta omega cross product with U, V, W minus gamma U, V and right. So this is a cross product. You can verify that those 3 equations can be written in this form. So I can write cross products out this. ठीक है, वो तीन इक्वेशंस जो हमने डिराइव की, these are differential equations, dynamical equations, or equations of motion in the block vector u, v, w. Now this expression here is a cross product, a vector and another vector, right? You can verify this by writing this as a determinant within some new axes. These new axes are now the Cartesian, the canonical axis in the Bloch sphere. Let's call that u, v, and w. Okay? One would be, so when you find out the relationship between u, v, and w, it will become clear that one of them is pointing along the x direction, the other pointing along the y direction, the third one pointing along the z direction. Okay? So if I take this vector omega r 0, the detuning factor u, v, w. This object here, the cross product with the negative sign amounts to this. And you can verify that this cross product will yield the same equations as you have over there. Alright? This is the damping part. We'll try to solve this quick. So let's just take a 2-minute break. Now the Bloch vector is changing with time, and the dynamical equation for the change for this Bloch vector is given by this cross product with some damping term. The damping is 0, this term, all of it goes to 0. Okay? So you get undamped oscillations. Let's see what kind of solutions we get. By the way, this term here, does this look familiar? This part, an equation of motion. If this is a position vector, suppose this is a position vector, what's this? A velocity vector. So velocity vector, generally, don't confuse now these notation. This is a velocity vector. For rotational motion, we know that this is angular velocity crossed with the position vector, right? This is dr by dt. Correct? So this equation is exactly similar to this. So this vector here represents the angular velocity with which this density operator is, the state is evolving over the density, over the Bloch sphere. So this is the angular velocity, and the angular velocity will be the length of this vector, which is sigma r squared plus delta omega squared under root, which is just the Rabi, this just the omega, capital omega, the detuned Rabi frequency. So the angular velocity for the system comes out straightforward as omega r squared plus delta omega squared, and we call this omega, which is the length of this vector over here. And the angle of rotation is, this is along the u axis, this is along the w axis. You will find out that u is related to the coefficient a in that, and w is related to the coefficient c. So this is the projection along the x-axis, this is the projection along the z-axis. Hence, this conforms with our original idea that for an off-resonant rotation, if I consider the Bloch sphere with an x, y, and z axis, then for off-centered rotation, the axis of rotation makes an angle xi with the z-axis, such that cosine of xi is delta omega, and or in other words, tan of xi is omega r over delta omega. If delta omega is 0, xi is 90 degrees, you have rotation around the x-axis. Right? So along z-axis, this component is proportional to delta omega, and this component is proportional to the Rabi frequency, the Rabi oscillation frequency. Okay? So everything works out. But now, if you solve this equation for different values of gamma, you'll be able to see what kind of oscillations do we get. So let's try to solve this equation on a software. Okay? Now, in certain cases, you can find analytical solutions. For example, undamped case, you'll be able to find an analytical solution. You'll be able to see that for an undamped case, you recover the result that rho BB is CB mod square is sigma r over omega r over sine square omega TO2. This will be a problem, right? So if you kind of put gamma equals to 0, you should be able to find out that this rho BB equals this. It never approaches 1 because now you're off resonant because you were delta omega, non-delta omega. So let's see all of these solutions for the damped and the undamped case. So in order to solve this equation, you need some initial conditions. Right? So what kind of initial conditions? So I can choose that initially all my atoms are in the ground state at A. So rho AA is 1. So what will be the initial condition for U? No coherences to begin with. U is 0 initially, V is 0 initially, and W, which is rho BB minus rho A is minus 1. So initially, in order when I'm solving all of this, I put U at time 0 equal to V at time 0 is 0. No coherences. Everything is along the z-axis. No coherences. And W at time 0 is minus 1, which means everything is in the ground state. Rho A is 1 and rho BB is 0. So I assume this. So when I put in these initial conditions, solve this equation for various values, let's see what kind of results we get. An undamped case. Okay. So what I do here is initially I define my 3 equations. In the undamped case, if you look at the first equation, and I'm on resonance. Suppose I'm on resonance, undamped case, nice case, I should get exactly the Rabi oscillations that we've been looking at in the previous lectures. So look at equation number 4 over there. Here. Equation number 4 देखें, ये वाली. Undamped case, on resonance, delta omega 0, gamma is 0. Right? Then I put in delta omega 0 and gamma 0 in equation 5 and 6. So that I've done over here. So I've defined the 3 equations. First equation, second equation, third equation. And I put in my initial conditions. So I define my system of equations. Then I solve the equations. So in this case, we've already done on a blackboard. This will give us sine square omega r t over 2. There is no delta omega, there is no damping. So I will get oscillations that go all the way up to 1, the Rabi oscillations, which are the top curve, the pink curve that I started off the lecture with. Right? So I saw these equations, U doesn't change. That's nice. The x component doesn't change because my rotation is also about the x-axis. My v component changes and my w changes as cosine tr. Now if I want to find rho BB is this w plus 1 over 2, which will be sine square omega rt over 2. Right? So I can plot this. Now I kind of have an off resonant and undamped. So now I detune. ये भी हमने क्लास में किया था. ये वाला scenario हमने क्लास में किया था, and we got that blue equation. CB mod square is omega r over omega, This is in the absence of damping but off resonance with some detuning. And we saw that the oscillations did not go all the way up till complete inversion. They fall short of it. But there were still oscillations. Right? So then I write down the equations, I include the off resonant terms, deltas. I don't write delta omega, I just write delta in my code here. For convenience, I define my equations, then I solve the equations, and I look at W. Okay, this is my W. This is the solution to my W. Okay, now from this W I derive my rho BB. Right? So when I do that, so here, this is my W, I add 1 to it and divide by 2, which is this thing over here. देखो blackboard पे right में W में 1 जमा किया और 2 से divide किया गया rho BB. So I get my rho BB. This is my rho BB as a function of time for arbitrary times, arbitrary detuning factors, arbitrary Rabi oscillation frequencies. Now I want to plot this by varying the deltas. Okay? So I choose my Rabi frequency to be 1 unit, just 1 unit, and my detuning to be some factor of that 1. If it's 0, I have on resonance. If I have delta equals 1, then I have 45 degrees xi. So I'm moving away from the equatorial plane towards the z-axis, and my detuning is going up. So when I plot this, notice that this sinh of this thing is sinh of iota times omega t over 2. Sinh of iota times this is actually a sine function. Okay? So I plot this, and I get, for varying values of off resonance, I get this nice curve. So still no damping, but I'm seeing oscillations. I keep on seeing oscillations. The blue is when there is no damping. There is no damping anyway. Blue is when I'm on resonance. देखो on resonance है मेरी oscillation rho AA से rho BB तक जा रही है, फिर rho A फिर rho BB. Right? Perfect inversion is possible when I'm on resonance. And as I move away from resonance, two things happen. The first thing is that the height of these peaks goes down, which means I do not get the complete inversion. All my states do not excite to the excited state. It's impossible to do a complete inversion, no matter how strong a field I apply. The other thing, so these peaks go down and down. The other thing that I see is that the frequency of the peaks goes higher. Off resonance, the blue peak, which is smaller, kind of has a higher frequency. So the difference between this point and this point is shorter in time. So the frequency goes up. I know that omega is greater than omega r. So my detuned Rabi oscillation is higher in frequency than the on-resonant Rabi oscillation. Omega is greater than omega r. So I see this effect. Now I include the factor of damping. So now I have damped and on resonance. Okay, so I go step by step. I have damped and on resonance. So I write down my equations once again. And I plot my beautiful. I am on resonance. Equations, damping on resonance. Okay. Let me run this again. Alright. So now let's look at this scenario. On resonance, damped. The blue curve is when there's no damping. The top curve is when there's no damping, Rabi oscillations. But now I successively increase the damping from 0.02, 0.2, 0.4, all the way up to a damping rate which is equal to the Rabi oscillation. Now what I see is the number one, the peaks get smaller and smaller, and for very high damping, the Rabi oscillations are only seen for a very small amount of time, and quickly you achieve saturation. Yes, please. ये नीचे वाली
उसको आइंस्टाइन वाली ग्राफ से मैच करना चाहिए, तो वो ये कि वो 0.5 तक नहीं जाएगा उसका एम्पलीट्यूड।
ठीक है, अगर आप इस गैमा को और बढ़ा देंगे ये मैच कर देगी। क्या चीज? मैं सारी चीजें समझाता हूँ, एक मिनट सारा कुछ समझाता हूँ। First of all, observe the following. So this is when high damping is there, you do not see oscillations. You hardly see oscillations, and that too for the shorter periods of time. Saturation is achieved much quickly. The rho BP is kind of settles down at a value of 0.3, roughly 0.3. If your damping is large, this saturation is achieved very quickly. Now if you look at these red curves, and so when you were looking at the Einstein rate equation, there were two regimes. When the u omega approached infinity, right, which means the Rabi frequency was really, really high, and which means that damping is really, really small. The Rabi frequency is high as compared to the damping. Then you achieve a maximum inversion of 0.5. So this is roughly this red curve here. So let me plot all of these. So still there is some damping. Let me plot all of this for longer periods of time and see what kind of asymptotes do you get. And you also remember that if your u omega was equal to the us omega, which is a saturation energy density, when the rate of stimulated emission and spontaneous emission were equal, then your maximum population that could be achieved was 1 by 3. This is that 1 by 3 that you see over here. In fact, you can predict these saturated values. How can you predict that? You can take equation 5, 6 and 7. Probably I'll do this in the next class, it's important. Take equation 5, 6 and 7 and put the left hand side equal to 0. That's what happens in saturation, because when du by dt is 0, dv by dt is 0, dw by dt is 0, you achieve saturation. Nothing changes. So put these equations 0 in the left hand side of equation 4, 5 and 6 and solve for u, solve for v, solve for w and see what values of w do you get. Okay, you'll get 1 by 3 and 1 by 2 in certain instances. So this is a good problem, and in fact I intended to do this today but I don't have time for this. So let me plot these curves for longer times. So instead of t0 to 25, let me plot these for t0 to 300. Say longer times. 300 Rabi oscillations have occurred. So now this is not very clear, so let me plot a small section of this. So now I plot this for longer times, the same curve for longer times, from 250 to 300 seconds. In 200, so the Rabi frequency is one unit. So this is 200 to 300 oscillations have occurred. Now blue represents no damping whatsoever. So this is the idealized hypothetical scenario when there is completely perfect Rabi oscillation. But even if I have a small amount of damping, 0.02, which is 2% of the Rabi frequency, then I get this kind of odd, this curve, this brownish curve. Still it has some oscillations, but now it's plateauing off to 0.5. Now this is because the Rabi frequency is about 40 times higher, or 45 or 50 times higher than the damping frequency. Very large, very intense fields. Or the damping is very small, or the applied field is very intense. Omega R really shows you the applied intensity, because omega R has an E naught term in it. This is the applied electric field. Okay, so very intense radiation has been put onto the atom, and some oscillations still persist all the way up to 300 seconds, 300 units, but they are plateauing off at a value of 0.5. If I increase gamma a bit further from 0.02 to 0.2, I make it 20% of the Rabi frequency, I get this nice oscillation slightly less than 0.5. And if I make the damping really, really high, no matter how intense a field I apply, if my damping is high and a considerable fraction of the Rabi frequency, I kind of hover around 0.3-ish. Okay, so this is how the Einstein rate equations and the Rabi oscillation concepts merge. If it's difficult to see Rabi oscillations because damping is always at play. So you need either very intense electric field that can create a large Rabi oscillation frequency, or you have to control the damping somehow. Okay, so if you want to see a coherent process occurring in a two-level atom, you really need intense electric fields. But intense electric fields have their own problems. These are called saturation problems. So I'll probably spend the next 15-20 minutes in the next lecture on studying this saturation. So I hope I've explained the optical Bloch equation in a very clear fashion. Okay? So inshallah next time we're going to start quantization of the